Welcome to your final exam review. As we go through these questions, I hope you'll appreciate just how much you've learned over this semester. You will find that all of these topics will be on your final exam. This first one is a limiting reactant problem and asks how many moles of sodium chloride can be produced when you have 5 moles of sodium reacting with 2 moles of chlorine. So I trust you remember to draw 1 circle for each mole of sodium and 2 dumbbells for each mole of chlorine, and then circle the atoms that represent the product. How many circles can you make? This next one asks, how many protons, neutrons, and electrons are there in titanium with a mass of 47 and a charge of 4+? So I trust you're going to visit a periodic table and see the 22 on top of titanium. So I can rewrite this with the 22 for the atomic number. And I trust you remember that for the number of neutrons, we have to take the atomic mass minus the atomic number, and that the number of electrons is equal to the number of protons minus the charge. This tends to be a challenging question for students. This is ranking things for number of atoms. And the trick here is instead of finding the sample with the fewest atoms, the answer will be the same if we find the sample with the fewest moles of atoms. Our first sample is in grams, so I'm going to need to look up the atomic mass of selenium. We can see that the mass of selenium is 78.96 grams per mole. So it's true to say that there are 1 mole of selenium atoms in 78.96 grams of selenium. So my first one is 2 moles of atoms. For my next one, remember that there are 8 moles of sulfur atoms in 1 mole of S8. That is a true ratio of 1 divided by 1. For the next one, remember there are 5 moles of atoms in 1 mole of sodium nitrate. The last one I can simplify. I know Avogadro's number is 6 times 10 to the 23rd, so clearly I have half a mole of nitrogen molecules. And it is a true ratio to say there are 2 moles of nitrogen atoms in 1 mole of nitrogen. How about the Bohr model of the atom? We want to know which letter represents the absorption of blue visible light. First off, remember that absorption means the arrow goes out from the center. Emission would be arrow in. Also remember that ultraviolet light, the arrow starts or ends at 1. For visible, it starts or ends at 2. And for infrared, the arrow starts or ends at 3 or 4. Finally, you have to remember that blue is high energy visible light. Red would be low energy visible light. Next one, what are the N and L quantum numbers for the highest energy electron in bromine? We'll need to consult the periodic table again. Here is our bromine at atomic number 35. We see that it's coming off row 4. And you might have to pick up that periodic table that you labeled with your S, P, D, and F blocks. What we're looking for is the row number and the block letter where the atom is located. Don't forget that if you're asked something in the D block, it's row number -1, and the F block, it's row number -2. This next question asks the valence electron configuration of indium. Remember that a valence configuration is your outermost S and partially filled orbitals. So let's visit a periodic table. Here is indium, and it is coming off row 5. Of course, you're going to be asked about electronegativity because it's very important to understand electronegativity differences, bond polarity, and intermolecular forces. So let me circle these on the periodic table for you. Here we are with lithium, nitrogen, neon, potassium, and selenium. Which one is the most electronegative? Maybe you'll have to refer to that periodic table that you had all labeled. Choose the chemical compound in which nitrogen has the lowest, which means the most negative or closest to negative oxidation state. Here is an example of the oxidation state rules from a previous test. This is the set of rules we work with. So remember, the oxidation state of the atoms in an element are all 0. Fluorine is always assigned an oxidation number of -1. Group 1A metals are +1. Group 2A metals are +2, and aluminium is +3. Hydrogen is +1 when bonded to nonmetals. Hydrogen is -1 when bonded to metals. Oxygen is assigned an oxidation number of -2, and group 7A elements are assigned an oxidation number of -1. Remember, the rules have to be applied in priority order, so Rule 1 is more important than Rule 5, and other elements take their cues from these rules. So let me do a sample one for you, just so you remember. How about the nitrite ion, which is not one of our choices? We have two elements, and remember, they need to add up in their oxidation states to the charge on the ion. So nitrite would have to add up to -1. We know from the oxidation state rules that oxygen within a compound is -2. So that gives us a -4 for both oxygens, which means, solving the math, the nitrogen has to be a +3 oxidation state. This next one also requires some knowledge of the oxidation state rules and other things. We want to know the IUPAC name for chromium with 3 oxygens. Remember that chromium is in the transition metal block, so it has multiple options for the oxidation state. We know that the sum of the oxidation states needs to be 0 because this compound is neutral, and that oxygen in molecules is typically a -2. This next one wants to know which ions below are isoelectronic with argon. So remember that a positive charge means you remove electrons, and a negative charge means you add electrons. You will be drawing Lewis structures for this test, so it's worth it to practice again. We'd like to choose the best structure for the bromate ion. First, let me remind you of how to calculate bonds. Your electrons required is going to be your number of atoms in the molecule times 8. Your valence electrons will be the sum of the valence electrons of each of the atoms, and you need to remember to subtract the charge. So this would be bromate with a -1 charge, so a -1. I'm sure you can figure that out. The shared pairs equals the electrons required minus the valence electrons divided by 2. And the lone pairs equals the valence electrons minus 2 times the number of shared pairs, and that can be divided by 2. Don't forget that we get the formal charge using the formula group number minus possession number, and to determine possession number, we divide the bonds equally. Once you've made your choice for the previous question, let's think about the bond angle, molecular shape, and hybridization. So you may have to pull out that master sheet from Chapter 6 that helped you relate the number of electron regions to these different properties. Here is a question where students need to use formal charge and their knowledge of Lewis structures to choose the best structure. The best structure is with all atoms at 0 formal charge. But if you can't achieve that, then at least try to get all the formal charges as close to 0 as possible. And if you have a negative formal charge, make sure it's on the most electronegative atom. This question wants students to identify the sigma star overlap. I trust you remember the star means it's an antibonding orbital, and the atoms are in the center of the lobes. So for sigma overlap, we need to focus on the area between the two nuclei. Remember that sigma overlap is head-on, and pi overlap is sideways. How about a gas law problem? We want to know the pressure of a 2-liter container filled with 5 grams of chlorine at 25 degrees Celsius. So some cautions before you calculate this. N is the number of moles of gas, and don't forget you're dealing with Cl2, not Cl. Also, be sure to convert your temperature to Kelvin and to select the correct R value. Your answer is requested in atmospheres, so that should tell you something about which of these R values to use. Here's a question about which species below has the highest boiling point. These are all molecules, so we need to play the game dispersion, dipole, H-bonding. Of course, you need to decide if the molecule has a polar region to decide if it has dipolar forces. And for H-bonding, you need to identify hydrogens attached to nitrogen, oxygen, or fluorine. And of course, the species with the highest boiling point will have the most intermolecular forces. This is a question about ionic structure and unit cells. As a reminder, corner sites count for 8 times 1/8 of an atom. Edge sites count for 12 times 1/4 of an atom. Face sites count for 6 times 1/2 of an atom. And center accounts for 1 of each atom enclosed by the unit cell. How about some thermo questions? What is the approximate value of delta S for the reaction below? And of course, you should compare the moles of gas in the reactant to the moles of gas in the product. Certainly you remember bond enthalpy questions, so we'd like to practice by getting the enthalpy change for this reaction as shown. Here's the table in case you need to rewind and access it. Let's look at the actual reaction. One thing that could simplify your math is to circle the areas that we don't change. The formula needed to calculate this is the sum of bonds broke minus bonds formed. And don't forget to draw the Lewis structure of the oxygen molecule. You need to know if that bond is a single, double, or triple bond. Here's a question asking about this particular reaction and when it is extensive. We're given the sign of delta H, that is negative. As in the previous question asking for entropy, we can look at the moles of gas on the reactant side versus the moles of gas on the product side. And somewhere in your notes, you should have this little table that tells you something about delta G relative to different algebraic signs of delta H and delta S. Here is a reaction coordinate diagram, and we'd like to choose the value of delta G and the energy of activation forward. Remember that for delta G, we're going to take the energy level of the product minus the energy level of the reactant. For energy of activation forward, we're going to take the energy of the transition state, which is the top of the hill, minus the energy level of the reactant. Ah, yes, the interpreting the reaction coordinate diagram question. Remember that when the energy of activation forward is greater than the energy of activation reverse, the rate constant forward is less than the rate constant reverse. These are opposites. In thinking about K, you can think about this as an old-timey balance. So clearly, this balance is skewed toward the reactant side and has more material as a reactant than a product. And of course, K's ratio is equal to the concentration of products divided by reactants. So that'll help you think about that one. For bond strength, Remember that the lower in energy something is, the more stable and stronger it is. It may help you to relate this to what you already know about the relative enthalpy and entropy of solids, liquids, and gases. Solids have stronger intermolecular forces and bonds. They're at lower energy. Gases have weaker intermolecular forces, and weaker bonds are higher in energy. For this last question, it helps to think about these diagrams in terms of enthalpy. Delta S is typically not very important for numerous reactions unless they involve a lot of gas in them. So it's pretty safe to assume that delta G is guided by changes in delta H for this reaction. So this is a diagram where we're going upward in delta G. So delta G is positive and delta H is probably also positive. So we can think about this diagram as endothermic, which means energy or heat is on the reactant side of the equilibrium. So if we add heat to this reaction, which way will it push it? I hope you say toward the product. That will help you answer situation D. How about some Le Chatelier's? We want to know the effect of cooling this reaction on our water concentration. Under these conditions, we have water in the gaseous state, so there will be a change in this if we affect the equilibrium. So delta H is positive, another endothermic reaction for you. And if we cool the reaction, that's like removing heat. So think about which way removing reactant will shift the equilibrium and what that will do to the water concentration. Another Le Chatelier's scenario. We're going to add more H2 gas to this reaction. We're adding reactant. Which way will this shift and what will this do to the water concentration? I'm sure you know this lovely question. It's actually a Hess's law question for those of you who have had prior chemistry. We don't explicitly talk about Hess's law in Chem 101, but we set up the stage so that you'll certainly understand it if you go to Chem 201. So this question gives us sublimation, which is a solid going to gas, as being plus 72.6. And it wants to know the enthalpy for this reaction, which is gas to solid, so it's reversed, and also has greater amounts. Ah, yes, ye old concentration question. It's important in this question that you actually know what barium acetate is. Barium is in column 2, so it has a +2 charge. Acetate is C2H3O2 1-. So you should think about the reaction stoichiometry and the ratio of acetate that's in solution when you answer this. And of course, you have most of the makings of how to figure out molarity. Molarity is, of course, moles per liter. Hopefully, a precipitation reaction will be fresh for you, since these just occurred on test 4. You're being asked about lead 2 perchlorate and aluminium sulfate, mixing those solutions together. So we need to think about lead 2 with sulfate and perchlorate with aluminium. And just so you don't have to dig through your notes, let me show you the solubility rules. So I trust you notice that perchlorate is in rule 2 and soluble with most things, but rule 4 with sulfate might be of interest to you. Hopefully, redox is also familiar to you, just coming off test 4. And the important thing about redox is to actually circle what you have on the redox table. So it's important in this question to recognize that you have solid aluminium, copper 2+, and Br 1-. Here are those actual reagents highlighted on your redox table. How about an acid-base question? What if the aqueous solutions of carbonic acid and lithium fluoride are mixed? Let me remind you where those are on the acid-base table. Here is the carbonic acid and the fluoride ion in their locations on the acid-base table. Don't forget, our equilibrium constant is going to be the Ka of the reacting acid over the Ka of the produced acid. And we use a single arrow to the right if the equilibrium constant is greater than 1,000, and an equilibrium arrow if the constant is less than 1,000. So those are some of the highlights of Chem 101. I hope you found this review helpful. And of course, good luck and good calculating on your final exam.